Dear students, you are most welcome in this class. I continue the same topic, methodological interpretation of fertilizer experiment, and I have already started this lecture, and references were already given to you. You know the yield depends on growth, and finally farmers or growers are interested in getting maximum economic returns. And they want to reduce the cost of cultivation. They want better use or efficient use of inputs, particularly nutrients or fertilizers. And then how much nutrient to be added into the soil to get the optimum yields and optimum growth. So I discussed that visual plant diagnosis can be done, plant tissue tests can be done, chemical analysis can be done for plant as well as for soils, critical values. But these approaches are not sufficient to guide a farmer to decide the optimum dose of nutrient, and not just nutrient, optimum dose of seed, herbicide, any other input. So most of the time, these are to be decided by field experimentation. So we restrict here just for nutrients or fertilizers. Then we conduct the field experiments. So field experiments are conducted having different doses of the fertilizer. And you can also have 2 or 3 different sources of the nutrients, combination of nutrients. So here, just I am showing you a simple fertilizer trial where only one nutrient is taken. So you conduct a fertilizer experiment, you take different doses of the fertilizer and you record the data, yield data. Results are obtained. And then you go for statistical analysis or you go for F-test. F-test means ANOVA, analysis of variance. And then you see your results are significant. If your results are significant, then you go for correlation and regression analysis. Here results are significant means, do we have any significant influence or effect of treatments or treatment variables? For example, you have taken nitrogen levels. So if the effect of nitrogen level was significant on the yield, then we say that results are significant. If you get significant results, then you go for correlation and regression analysis. Through correlation and regression analysis, we can find a line, we can find a curve, we can find an equation or model. You can call it model, equation, or curve or line. And then that is called as response curve fitting. And once you have found out the response curve, then you can apply certain economic principles to determine the optimum level of fertilizer. So response curve, I already started. It is functional relationship between input and output. It was explained to you. And there were different types of response curve, linear, quadratic, cubic, quadratic, and these were all shown to you. These curves, different curves like quadratic curve, you can see the shape of the curves, and exponential equations are also there, where variable itself is the exponent. But we restrict only to the polynomial equations. So you see exponential equations, polynomial equations, and polynomial equation is an expression consisting of variable, coefficients, components. And you remember your high school days when you used to solve polynomial equations. And you know, in polynomial equations, the exponents are numbers, are positive integers. The independent variable can occur multiple times. Different x's are separated by addition, x power 1, x power 2, 3, and so on, in polynomial equations. I've already shown you polynomial of degree 1, polynomial of degree 2, 3, and so on. So these equations were discussed, and polynomial of degree 2, 3, 4, 5. Polynomial of degree 1 is linear, and polynomial of degree 2, 3, 4, 5 is called as curvilinear relationship. Curvilinear. One is linear relationship, other is curvilinear relationship. And you can also call it non-linear. That means it is non-linear, or curvilinear relationship when you have 2, 3, 4, 5, etc. And they represent different versions of the law of diminishing returns. And then you can go for economic interpretation once you have the curvilinear kind of relationship. Now we already discussed this issue, and you see these are the levels of nutrient, levels of nitrogen, suppose, and on y-axis you get response. Response with respect to growth or yield. You can have some dependent variable. On y-axis we have dependent variable. On x-axis we have independent variable. So at each level of nitrogen or at each level of independent variable, you must have recorded certain yield or certain response or certain growth parameter for each level of independent variable. Say for 0, you got this point. For 30, you get this point. For 60, you get this point. For 90, you get this point, and so on. So you got different points directly for paired data. This is paired data. For every x1, x2, x3, you have y1, y2, y3. So main problem here is that we cannot join these points. We cannot join these points. They are not allowed statistically because we have data for 180 kg. We have data for 210 kg, but we do not have data for 190 or 200 or 205 and so on. So if you join these points, the predictions will not be correct, statistically correct. So what statisticians say that these data, if you cannot join, then you should find a line that can represent this data very well, and which is called as response curve fitting or regression analysis in this case. So actually the main purpose of fitting this line or to identify the line or to identify the equation is to make predictions, predicted values. So for this, we can draw several lines, and one of the best fit we need to decide. So no straight line will exactly pass through all the points, although many can be drawn. I will show you how many lines can be drawn. Find the straight line which fits all points better than all. Now, which line will better fit the data? We need to find out the value of A and B. Statisticians have solved our problem. If equation is y is equal to a plus bx, and you can find out value of A and B through some regression analysis or statistical technique, then that equation will be the best fit. That will be the best fit. Can we decide a measure of all closeness of the fit of the various lines which can be drawn? It is also possible that data follow the diminishing kind of curve, wherein non-linear regression would be better fit. So suppose you have got a scatter plot of independent variable and dependent variable. They are paired, and you get some scatter plot, and that can give you some idea whether it is giving positive correlation or negative correlation or no correlation. If there is no straight line, then you can think of having curvilinear kind of relationship. That data may represent the curvilinear kind of relationship. So the response curves are fitted by method of least squares. I already discussed, just refreshing your memories, a statistical method used to determine a line of best fit. A line of best fit by minimizing. Minimizing here means by reducing the sum of squares created by a mathematical function. Means sum of square of distances from the predicted line should be the least, the minimum. That line is the best fit, and the method is known as method of least squares because you are squaring the distances. In this case, some values of the difference of actual data and predicted data may be positive. In some cases, it may be negative. So therefore, you need to square and total all the sum of squares. And then the line which is giving you the least value of the total sum of square is the best fit. So a square is determined by squaring the distance between the data point and the regression line. So this equation you can also call as a regression line. if you make it a line, if you convert the equation into a line or into a curve, then it is your regression line. So it is just terminology. Terminology, most of the time things are same, we are not able to understand it. So here you see, this is the original data, and for original data, you also call it observed data. Observed data or original data or actual data. These three terms are equivalent. You can call observed, actual data, or this original data. In figure number 2 also, you see this is the same original data. In figure number 3 also, you see it is same original data. But I have drawn three different lines across, just randomly I did it. So now what you can do, you can measure the distance. This is the predicted value. This is the predicted line. And the data on this line are also called as expected values or predicted values. So here, this is the point. So you can take the difference. So here you must be having some value, and that is your expected data. You can represent it by a small y. And this is your actual data. This is your actual data, and you can take the distance. You can measure it very easily. And then from this point to this point, the difference. From this point to this point to, and all these points. And here you will see the observed value is less than the predicted value. Predicted line, the data here is more than the actual data, observed data. Then you will have values in negative. The difference means capital Y, that is observed value, minus predicted value. So here you will have minus, the distance in minus. Similarly, here also you will get distance in minus, because this is your actual data, this is your predicted data, and if you take the difference of these two, it will be in minus. So therefore, you take the difference and square it. Similarly, here also square it, here also square it, and take the sum of total of all the sum of squares of distances. Then similarly, you do the same exercise for this, another line, and you find out the value of sum of squares, total sum of square of distances, similarly in the third line. So the line which is giving you the least values of the total sum of square of distances is your best fit. And this is the method of least square. And what statisticians have done already, they have given us the equation y is equal to a plus bx. So here, this is our predicted equation. And here, if we can find out the value of b and a based upon the observed data or actual data, we can find out the equation. Now, to get more clarity, same thing is explained here. You see green line. This is assume the best fit line. Assume here it is the best fit line, and it has different values. I represented here with a small y and green. So y0, y1, y2, these are your predicted data. Suppose these are predicted data. And the black one or blue lines, this black one, y0, y1, y2, y3, these are your observed data. And some are below the line also, some are below. So measure these distances, take the sum of square, total it, and it will be having the least value. No other line will have that much of least or lowest value of total sum of square. Therefore, that line will be the best fit. Now, for more clarity, you can make a table like this. This is your output, or this is your observed data, actual data, or original data, represented by capital Y0, Y1, Y2. This is control. This is say 60 kgn, 120, 180, whatsoever. So you can have these values in numerical terms. And then expected values. Expected values are on the line, which is corresponding to observed data y0, y0, y1, y2, small y1. And in the end, you can have yk, many pairs. Then you can take the differences between these two, capital Y0 minus small y0, these differences. Similarly, for the next pair, next pair, next pair. And finally, yk minus yk, small yk. And you square individual value. You need to square the individual value and then take the total of that. Take the total of them, that this like this, you square it, and then it should be minimum. Yk minus yk whole square should be minimum. Now, in this case, you have seen that the line is passing, not exactly passing through the observed data, not exactly passing through. This is your observed data. It is deviating. Deviating. Some are the differences. So some data is away from the predicted line. So those are the residuals. Means data which remain unrepresented is your residual. Here, residual is equivalent to error. It is also called as error. So in regression analysis, the error is the difference in the observed y values and the predicted y values. That difference, the last time you can see this. This is also called as error. This is the difference of actual data and predicted data. In regression analysis, the error is the difference in the observed y values and the predicted y values. Residual is actually the distance of a point from the curve. A residual is positive when the point is above the line or above the curve, and it is negative when the point is below the curve. I have already shown you positive. This is your negative value, and these are positive value. The points which are above the line are positive. Differences are positive, but here differences are negative. Now you see more clearly the residuals. So these are the residuals. The red lines representing here are residuals. And in general, if your equation is genuinely linear, then if you take the total of all these, it will be zero. Therefore, later on you will see it is again residual sum of a square. You will find some new thing. That is your error. So residuals are shown in red. So these blue are your original data. And in this line, these are predicted. This is predicted line. So here you will get predicted data, and the distance. Now, as I told you that through correlation and regression analysis, we can easily go for response curve fitting. So response curve fitting, to get the idea of response curve fitting, we must have some knowledge of the correlation and regression analysis. This knowledge will help us to find out the response curve, to fit the response curve. So just some slides on correlation and regression analysis. So what is correlation analysis and what is regression analysis? Now just I want to know from you, what is the difference in correlation and regression? Forget about the analysis. What is the difference in correlation and regression? Anybody? What is the difference in correlation and regression? Can anybody tell me? Arijit?
Yes, sir.
Yeah.
Sir, correlation means, sir, there is a relation between input and output, like that. The input will correlate with the output, so that if we apply input, then the output will be high, like this, sir.
Okay, good. You made an attempt, and good attempt. And what about regression? So any other student can try. Sneha?
Yes, sir.
Any idea about difference in correlation and regression?
Sir, in correlation, there are two variables generally in which we predict the relation between them, whether it's an independent, positive or negative. In regression, generally, regression term literally means we look back. And I think we predict the conditions according to that.
Okay, that is looking back or downgrading or degrading or going less and less, something like that. That is okay. So actually, in correlation, you just want to see whether two or more variables are related. Are they related to each other? And in regression analysis, you just see the nature of the relationship, the mathematical relationship. between two or more variables. If you make 1 unit change in X, then how many units changes are there in Y? Normally, they go on decreasing. So, for example, in general, people started with height of a family people and their weight. So they made studies whether height is related to weight. More height, does it mean that more height means more weight? So such kind of variables are studied in correlation, whether two variables are related to each other or not. That is your correlation. And regression is actually nature of relationship. How numerical these two variables or more variables are related to each other. The quantitative change in Y associated with the unit change in X is called as regression. Is it clear? The quantitative change. Suppose you got one equation. In equation is your Y is equal to A plus BX. So you can go on changing the value of X. Value of X, you can have 10, 20, 30, 40, 50. And then you can see how much change is there in the Y. So if you change the value of X in the equation, the change will be there in the Y also. So how much is the change? What is the quantitative relationship between these two variables is your regression. Is it clear? Regression and correlation, quantitative relationship. So now correlation analysis provides a measure provides a measure of the degree of association, how closely two variables are related, a mutual relationship or connection between two or more things. So correlation is a statistical technique that can show whether and how strongly pairs of variables are related. It can just show you the strength of relationship. It cannot show the numerical relationship of variables. So in regression analysis, it describes the effect of one or more variables, independent variables, on a single variable, that is dependent variable, by expressing the latter as a function of the former. So you can see you got some functional relationship between two variables in regression analysis. Y is a function of X. So you can have here another variable Z also. You can have two or more independent variables can affect one dependent variable. Then the relationship will be multiple regression analysis. And if you take only two variables, one dependent variable, other independent variable, then that will be simple regression analysis. Only two variables, simple regression analysis. If many variables affect the dependent variable, then it is multiple regression analysis. In experiments on yield response to nitrogen, yield is dependent variable and nitrogen rate is independent variable. So it depends upon your choice which variable you want to make dependent and which variable you want to make independent. For example, in plant, you have leaf area, and you also have number of leaves. So here you are not sure. It depends upon your interest that your leaf area and number of leaves, which variable you want to make dependent and which variable you want to make independent. Suppose A student thinks that leaf area is affected by number of leaves, means more the number of leaves, more will be leaf area. But other student can take it otherwise also. Okay, for me this if I have more leaf area, then I will have more number of leaves. So you can interchange. It depends upon your interest. You can make leaf area as a dependent variable and number of leaves as independent variable and vice versa. So many times it is the researcher who can decide. However, the strength of relationship will not change. The value of the correlation coefficient will be the same. If you change the variable, convert the variable independent into dependent and dependent into independent, the strength will not change. The correlation coefficient which measures the strength of relationship will not change. So regression analysis is a method for investigating investigating functional relationship among the variables. Or otherwise, you can define regression analysis, the process of finding a mathematical model or equation that best fits the data in regression is your regression analysis. Dependent and independent variable. I think you know dependent variable and independent variable. The variable to be predicted, that variable you are going to predict or model, say y, is called the dependent variable or response variable. The variable used to predict or model y are called independent variables and are denoted by symbols x1, x2, x3, etc. It is also called as predictor or explanatory variable. The variable whose outcome depends upon other is your dependent variable. Correlation exists between, okay, we go to the next link. Now we continue to see a correlation exists between two variables when one of them is related to the other in some way. So this is the definition of correlation. A correlation exists between two variables when one of them is related to the other in some way. Then a scatter plot or a scatter diagram, it is also called as a scatter diagram, is a graph in which the paired sample data are plotted with a horizontal x-axis and a vertical y-axis. You see, if you have seen a scatter plot, you have paired observation, paired data. For every x, you have corresponding y. So each individual pair is plotted as a single point. You see, this is scatter plot. For example, this 10. So this is blue. This blue is representing x, y, both x and y. So this is a kind of scatter plot, scatter diagram. You must have seen it. The linear correlation coefficient. Now, how to measure whether two variables are related or not, and then how closely these variables are related. So to know the relationship of two variables, we work out the linear correlation coefficient, or you can simply call it correlation coefficient. So it measures the strength of the linear association between the paired x and y quantitative values in a sample, sometimes referred to as the Pearson product movement correlation coefficient. So to give credit to the Carl Pearson, who originally developed the formula for correlation coefficient. So it is also called as Pearson product movement correlation coefficient. Now, simple and multiple correlation and simple and multiple regression analysis. According to the number of variables involved in functional relations between the dependent and independent variables. It is simple correlation or simple regression if only two variables are involved. One is dependent and one is independent. Then if you do correlation and regression analysis, these will be called simple correlation and simple regression analysis. If you have more than two independent variable, two or more than two independent variable influencing one dependent variable, then it will be multiple correlation analysis or multiple regression analysis. The procedure is termed as linear if the form of the underlying relationship is linear and non-linear also. So you can have non-linear relationship also, or you can also have linear relationship of two variables or more variables. I've already given you very good notes, so you can browse those pages and see to get more clarity on this subject. But one thing I wish to tell you again, that this is very, very important subject. Each one of you should know this subject. And if you know this subject, if you understand this subject, then you can learn many more things in your life, in your career. Now, to get some more understanding of correlation and regression, take, for example, following sayings. The bigger they are, the harder they fall. The more, the merrier. Easy come, easy go. The better the day, the better the deed. As the twig is bent, so is the tree inclined. So all these sayings of proverbs, you see there are two variables, there are two things. One is influencing the other. One is influencing the other. So each saying implies that two variable quantities, magnitude of one is depending on the magnitude of the other. One is influencing the other. They are called as independent and dependent variable. So one of them you can call independent variable and other as dependent variable. For example, to be merrier, to be happy, it is dependent upon what? The more. If you have more and more, which is your independent variable, the merrier, you become happier. So happiness or merrier, the nature depends upon the more. So each saying implies two variable quantities. Magnitude of one depends on magnitude of the other. They are called as independent and dependent variables. As one variable increases, so does the other. So there is direct positive correlation. You can see one is increasing, other is also increasing. Take another group of sayings. Much haste, little speed. Small pitchers have big ears. The best gift comes in small packages. So see, in this case, there is negative correlation. One is increasing or one is more, other is less. So here an increase in one variable is accompanied by a decrease in the other. So this is called as inverse or negative correlation. So you can see this is positive correlation, this is your negative correlation. X-axis you have X variable, Y-axis you have Y variable, dependent variable. Now, there can be a situation where you cannot have any kind of relationship. Two variables may not be related. They may not be having linear relationship. Means one is increasing, other is increasing. One is increasing, other is decreasing. So you can have that kind of situation also where you can say there is no correlation or not correlation, no linear correlation. There is no linear correlation, but these two variables can have non-linear correlation or non-linear or curvilinear kind of relationship. So a relationship between two variables for which the points in the corresponding scatter plot do not fall in approximately a straight line. So you cannot have a straight line here. Non-linearity. Therefore, it is non-linear. Non-linearity may occur because there is not a defined relationship between the variables as in the first two figures. In first two figures, you got very clear relationship, but here there is no linear relationship. Here you can say it is a non-linear or curvilinear relationship. Regression, as I told you, now you have good idea or fair idea about the correlation. Now see idea about the regression. As I told you, we need to find out the numerical relationship between two variables. So amount of change in one variable is associated with a unit change in the other variable. Please do remember these two lines to define the regression. Amount of change in one variable, mostly it is independent variable, associated with a unit change in the other variable is called as regression. Correlation refers to the fact that two variables are related and closeness of this relationship. Correlation only refers to the closeness of the relationship between two variables, and regression, on the other hand, refers to the nature of relationship, the quantitative relationship. See the following sayings. Now, just to explain to you about the regression, what does it mean? See these proverbs or sayings. A penny saved is a penny earned. A bird in hand is worth two in the bush. A stitch in time saves 9. One picture is worth 1,000 words. So here very clearly you can see in these sayings that there is some numerical relationship between two variables. Or you can say a penny saved means one penny saved means one penny earned. One bird is equal to two birds. Those who are in bush. A stitch in time, one stitch is equal to 9 stitch. You can say like this. So one picture or one y is equal to 1000x. So likewise, here you find some numerical relationship. So now you can see regression equations and coefficients between independent and dependent variable. This is very simple. Don't fear by seeing this complicated slide. It is very simple. Now you see the table. Independent variable is your x. And suppose dependent variable is y. And then what will be the regression equation? What will be the relationship between y and x? And then what is regression coefficient? Like last time you have seen correlation coefficient. Here it is regression coefficient. So you can see pennies. Just a minute. Yeah. I was just seeing. So you can see pennies saved in X, pennies earned. So here 1 penny. You see 1 penny is equal to 1 penny. 1y is equal to 1x. 1y is equal to 1x. So actually, or you can say y is equal to 1x. So here 1 is not shown here. You know it before this. And this is 1 is regression coefficient. If no number is given before a letter, that means it is multiplied by 1. You know this fundamental mathematics. So 1 is regression coefficient. And then hand birds, 1 bird in hand, 2 in bush. So you can see relationship can be written like this, y is equal to 2x. So here 2 is the regression coefficient, means 2 times x is equivalent to y. Therefore, this equation is your regression equation. And if you plot it, if you put it in the form of a picture or graph, then it becomes a line. Regression line is equal to 2. So here 2 is the regression coefficient. And 1y is equal to 9x. Here 9 is the regression coefficient. And 1y or y is equal to 1000x is your 1000 is your regression coefficient. So column 3 is headed as regression equation. These are equalities of a straight line. Y is equal to a plus b. They are representing y is equal to a plus bx. Of course, a is not shown here. It is just to explain you to get more clarity about the regression coefficient. The general equation of a straight line is y is equal to a plus bx. This is the equation. This is the predicted equation. You can make predictions if you find out value of a and b. And that will give you the least values of total sum of a square of differences in distances. The symbol A is called as the intercept. Here you see one more thing is your A. It is called as intercept. What does it mean? When x has the value of 0. When x is 0, then whatever value of dependent variable is there, that will be called as intercept. In nitrogen trial or fertilizer trials, the yield at control or x0 is your A, is your intercept. So since when x is the value of 0, y is equal to A. As the line crosses the y-axis at a units from the origin. Don't worry, you will get more clarity about intercept later. When A is 0, the line passes through the origin. It will go to the origin, means where you have x0, y0. For when x is 0, y is equal to 0. Now, regression coefficient and intercept continues. The symbol B is called the slope. You see y is equal to a plus bx. So B is actually regression coefficient. You have seen B is regression coefficient and A is intercept. So symbol B is called the slope since it determines the steepness of the line. So it is just like your marginal return. If you remember marginal return, it was delta y upon delta x. If you make 1 unit change in x, how much change is there in the y? So here also the slope is just like that. The symbol B is called the slope since it determines the steepness of the line. Means if you get higher value of B, more value of B, that means you are getting high response to the variable. If this value and the curve will be the line will be very steep. If the value of B is decreasing, then you will have the angle of the line will decrease. Angle of the line will decrease. So this is your slope. It determines the steepness of the line. So B is called as regression coefficient. It is easy to see that B is the amount of change in y associated with a unit change in x. So the value of regression coefficient is important. It is also called as slope of line. And what is required? Sometimes you need to test the significance of this regression coefficient. whether it is significant or not. Like you see the correlation coefficient, whether it is significant or not. You will learn it slowly, don't worry about it. So just for the time being, you remember what is meant by B. It is regression coefficient, amount of change in Y associated with unit change in X. Therefore, it is logical to call B the regression coefficient. Similarly, you will also have non-linear relationship or curvilinear relationship, y is equal to a plus bx plus cx square. In that case, b and c will be your regression coefficient. There you will have two different coefficients. Now, we start linear relationship. So I will finish in next 15-20 minutes. Kindly be attentive. Linear relationship. The relationship between any two variables is linear if the change is constant throughout the whole range under consideration. Means every time you get the same return, same change due to change in or unit change in x. So that is your linear relationship. The graphical representation of a linear relationship is a straight line. I have already shown you. The functional relationship between a dependent variable y and an independent variable x can be represented by a linear equation. You can see y is equal to a plus bx, whereas a is the intercept of the line on the y-axis and b is the linear regression coefficient. So instead of regression coefficient, you can also call it linear regression coefficient. It is the slope of the line or the amount of change in y for each unit change in x. And here the change will be constant. Therefore, you find a straight line, which is also called as linear correlation. Now, here again, for your convenience, if the intercept of a is 1, suppose y is equal to a plus bx, here your a value is 1 and the linear regression coefficient is 2. The value of b is 2. b is 2 means if you make change of 1 unit in x, there is 2 unit change in y. The relationship is expressed as y is equal to 1 plus 2x. So this 1 is your intercept. Y is equal to 1 plus 2x with the two parameters of the linear relationship a and b is specified. The value of the dependent variable y corresponding to a given value of the independent variable x within the range of x values considered can be immediately determined. Means you can very easily make predictions. If you have this equation, if you know the value of a is 1, means when you have value of x as 0, you will have 1, the value of y is 1, and then 2x plus 2x. This is the relationship. So you have nitrogen levels, say, if you have 0, so you put 0, you will get only 1. So y is equal to a. If you have some value like 20, 30, 40, you can put those values here and you can find out you can predict the value of y. So this is the basic purpose. So when there is more than one independent variable, say k independent variables, x1, x2, x3, xk, the simple linear functional form of the equation can be extended to the multiple linear function of the equation. Means if you have more than one variable, say x1, x2, x3, x4, etc., or you can have x or z or say a, b, c, d, whatever number you have, then you can have this multiple linear equation like y is equal to a plus b1x, b2x, and so on. You can go on adding. So here, this is one variable, this is another variable, and so on. And now regression analysis for linear relationship. Regression analysis tries to fit a model to one dependent variable based on one or more independent variables. In most cases, there will be error. There will be residuals. The goal is to minimize the errors or residuals from the actual data to the regression line. Here you want to minimize the distances. The least squares line minimizes the sum of square of errors or sum of square of residuals. The regression equation line helps to predict the values of the independent variable based on the given values of the, the regression equation or line, you can call it equation or line. It helps to predict the values of the dependent variable based on given values of the independent variables. So you can make predictions once you have estimated the equation. It is method of finding. What is simple linear regression analysis or response curve fitting? It is method for finding the line of best fit between the dependent variable y and the independent variable x. So many times I am repeating the same thing just to make you better understanding and for more clarity. So field experiments are conducted on a great variety of data, including crop yield. The recorded data are considered as observed values or actual data used to fit the regression model. So here you can take any input, not just fertilizer or nutrients, NPK or levels. Here you need to take levels of the input. If you do not take levels of the input, then you cannot go for linear regression analysis. These levels of input can be equidistant or can have unequal interval also. It does not matter, but levels should be increasing. For example, if you want to test the doses of herbicide, then you can test doses of herbicide against the weed dry matter or weed number, weed population. Doses of herbicide you can correlate to the grain yield, you can correlate to plant growth or any parameter. Similarly, fertilizer level, similarly irrigation levels. In some cases, you have applied 1 irrigation, 2 irrigation, 3, 4, 5. So you can have irrigation as independent variable and yield or any other parameter. You can take plant height also. On x-axis, you can take number of irrigation and you can take plant height as dependent variable. It is not necessary to always take yield as dependent variable. You can take any variable which is dependent upon x. So it cannot be just plant height. It can be your leaf number, leaf area index, or any variable you can consider as dependent variable. The recorded data are considered as observed value. You can record any dependent variable used to fit the regression model. And these fitted values give a regression equation or line that can be used to get the expected or predicted or estimated value. You have applied several irrigations, 1, 2, 3, 4, 5. What will happen if I apply 2.5 irrigation? So you can make prediction for 2.5 irrigation also. But before fitting any relationship between input and output or independent and dependent variable, it must be ascertained that the output or the yield or your observed data, actual data, due to different levels of input or independent variable has to be significant. Already discussed, method of least square is used to compute the linear regression equation. So here you want to compute the equation and that can be plotted as a graph. So that is computation of regression equation means, or regression analysis here means, with respect to linear relationship, that you need to find out value of A and B, intercept and regression coefficient. So here, just to explain you again, the method of least square should be the minimum. This is your actual data, the red one. Red one is your actual data represented by capital letter in blue, Y0, Y1, Y2, Y3, Y4. So you can see here Y0. When Y0, this is your, here you will have intercepts here. When X is 0, and then what is the value of Y? So here you get the A is here. When your X is 0, the value of A is touching the line, this Y-axis. So this dotted line is your predicted line or estimated line based upon the equation, and you can take the differences. Take the differences of distances and square those values. And here, the value of sum of square of total sum of square of differences will be the lowest value. Now, you see how we can do it. You try to understand it. Computation of simple linear regression equation. Input is your X. Suppose it is nitrogen level, N0, N1, N2, N3, or any variable. Then output or your dependent variable Y, it is not just yield actually. Y does not, here it is not representing yield only. Here Y is representing any dependent variable. So you can take any dependent variable. Suppose your independent variable, you get phosphorus levels in different soils, phosphorus level in different soil in increasing pattern, and then the yield or any say phosphorus uptake by the plant. Here you can take phosphorus levels and phosphorus uptake by the plant as a dependent variable. And then you have equation y is equal to a plus bx. So here you get expected values. From the equation, you can put the value of x in the equation, y is equal to a plus bx, and then you can predict the value. You can find out the expected values from the equation. That is your small y0. Expected value, y1, y2, yk. So these are pair data, and then sum of difference or difference between these two, output or your original data minus predicted data, y0 minus y0, small y0, and so on. Capital YK minus small yk. So you can have any number of pairs. So these, now you take the difference, you sum it, you square these values and take the total of all squares. And those squares should be minimum. Here I want to show you the residuals. This was your observed data. This is your predicted data. The difference between these two is your residual, or it is also error. Finally, you can see capital Y minus A plus BX whole square. This is called as residual sum of squares. So don't worry about it if you could not follow this table. I will explain it with the help of one example where it will be much clearer, much easier to understand. Otherwise, for the time being, if you have any question on this or up to now, you can have a discussion. So you are welcome to ask questions or anything related to this. Up to now, is it clear to everyone, or if you have doubt, you can ask. Hello, Shubham?
Yes, sir.
Do you have any doubt?
No, sir.
Abhishek?
Yes, sir.
Yeah, you have anything to ask? Anybody can come. See, for me, you all are equal. All are equal. The name I see on the screen, I'm not just a single making just. I'm not attacking any. It is not personal. I see the name on the screen and just I call. So don't take it otherwise. I just see the name. So everything is clear to you. This is the time. If you have any doubt, we continue.
Sir,
Yes.
residuals is just the difference between the observed and expected data, sir.
Yeah, exactly. And residual is the error, actually error, observed value and predicted value. So from the observed value, actually there is some mathematical work, that is regression analysis, through which we can find out the value of A and B. And then we will have equation. That is your estimated equation, or that is your regression equation. And which equation? That equation is representing the data, and we can use that equation to make predictions. That is important. And from in this, the value of the predicted value can be easily calculated, can be easily computed. So you have observed value and predicted value, which is from the equation. You take the difference between these two, and that difference will be residual. You take residual of all the pairs. And if it is truly linear, if the relationship is truly, genuinely linear, then if you make the sum total of all the residuals, that will be actually zero. So what statisticians do, as you know, usually they go for squaring the values to overcome such problems. So here these residuals are squared, and then their total is taken. This residual means y0 minus predicted value. Predicted value here, it is written a plus bx0, means what is the predicted y when x is 0. Next line, next row, you can see y1 minus a plus bx1. Here, this x1 is your level of independent variable, next level. And at next level, what will be the predicted value? So this a plus bx1 will give you predicted value. So then you take the differences between actual value and the predicted value, and whatever is left is your residual. So these residuals, the sum total is 0, therefore they are squared. And this is also known as residual sum of a square or error sum of a square, which is called as error sum. Is it clear? Residual sum of a
Yes.
square or error sum of a
Yes.
square? Okay.
Yes, sir.
So consider the linear following linear regression equation: y is equal to a plus bx. So in the above equation, x is independent variable and y dependent variable. Here we need to find out the constants, the values of a and b. A is intercept and b is your regression coefficient, or b is also known as slope. To do so, we need to compute the means and different corrected sum of squares. Now your regression analysis starts. Now you are going to find out the equation. You are going to fit the equation, or in other words, you need to find out value of a and b from the data given in the table. So in place of input, you can be given 0, 20, 30, 40, 60. In place of output, you can be given grain yield, suppose, say 10, 15, 20, 30, 40, 50. So you will get some numerical values, and then you need to find out the value of a and b. How to find out value of a and b, you will see later. So actually what happens there, so here you get the sum of difference also. Sum of difference also, y minus y, and then you can calculate the mean of this, mean of x. So in the first column, you have input levels. So you can calculate the mean of x. You can calculate the mean of y also, and then expected value also, and then you can take the difference of these two. So certain parameters can be worked out, which are also known as corrected sum of squares. So from this table, you can work out certain corrected sum of squares. So for input x, you take the mean and subtract the value of x minus x bar, and take the square. And for every observation, every pair data, you calculate those squares, corrected sum of squares, and make the total. Similarly, for y also you can calculate the total sum of squares. That is called as total sum of square, summation y square, y0 minus y bar. The mean, the respective means can be subtracted from the column number 2, and you get summation y square. So certain, then x into y, summation xy. So you can calculate certain parameters from this data, from the same table you are seeing, and then you can find out the value of a and b. So these formula you need to remember for regression analysis or fitting the regression equation. Mean of x, easily you can calculate summation x upon n. Similarly, mean of y, summation y upon n. I hope that you know how to calculate the mean of the data. And then corrected sum of square, summation x square. Remember, this is small x square, then summation x minus x bar. Here x bar is mean. And you see summation n. The n is number of pairs, how many pairs are there. And I is ith pair, first pair, second pair, third pair. So summation x square is corrected sum of square for independent variable, and y square is your corrected sum of square for dependent variable, and then cross product, sum of corrected sum of cross product, summation x minus x bar into y minus y bar. So these parameters are required to be to calculate the value of a and b. So I will show you later in the practical exercise. So then you can calculate value of b and a, summation xy divided by summation x square. This is the value of b, regression coefficient you can calculate, and then value of a, y bar minus bx bar. So from this relationship, once you have found out the value of b, regression coefficient from this relationship, then you can, by this, you can put the value of b here, and you can find out the value of a. You know the mean value of x. X mean and Y mean. So then what happens? Now you need to see the linearity of the equation, whether this equation is genuinely linear or not, whether the regression coefficient B is significant or not. You need to test it. And for testing it, you need to go for F test. You need to go for F test. So analysis of variance is your F test. I think everyone of you understand what is F test. It is ANOVA, analysis of variance. The variance in data or variance in Y or dependent variable can be partitioned into different components. There are different sources of variation. So here you are going to test the linearity of the equation. Suppose you have found out value of A and B, and you have put those values in the equation. Now you know the equation. Now you want to see whether this equation is genuinely linear or not. So you want to test the linearity of the equation, or you want to test the regression coefficient, the significance of the regression coefficient. So for this, you need to go for F test. So sources of variation here can be regression. One source can be regression, linear regression, or you can say linearity. Then degree of freedom is 1. Remember, if your regression is linear, where x power is 1, the degree of freedom is always 1. If you have quadratic regression or quadratic equation, then the degree of freedom is 2. If you have cubic regression, the degree of freedom for regression is 3, and so on. And total degree of freedom, as you know, is n minus 1. N is number of pairs of observation minus 1. So that is your regression, total sum of square, degree of freedom for total degrees of freedom. And you know, if you deduct the regression degrees of freedom from the total degree of freedom, you get a degree of freedom for residual or error. So n minus 1 minus regression degree of freedom, that is 1. You get residual degree of freedom as n minus 2. N minus 2. Now sum of square, for calculating the sum of square for regression or sum of square for linearity. So formula is summation y square L, or regression, you can say it SSL, sum of square due to linearity or sum of square due to regression. Very easy to calculate. Summation xy whole square divided by summation x square. Then total sum of square. You see total
Hello,
sum of
sir.
square. Yeah. You have
Sir, can you repeat the residual degree of freedom, how to calculate?
residual degree of freedom. Suppose in case of sources of variation, here in the regression analysis, you have two sources of regression. One is regression itself, source of variation. Other is residual. Residual is your error. Now, for degrees of freedom, in case of linear regression, degrees of freedom for regression is always 1. If you have quadratic regression, then degree of freedom is 2. And if you have cubic regression, degree of freedom is 3. It depends upon the polynomial. If it is linear, means linear polynomial is 1, 2, 3, 4. And actually, what happens in this case, I discussed with people in IESRI that what is the reason why you give degree of freedom if it is linear 1, quadratic 2, and so on. I didn't get the answer. So if anybody get answer, then please share with me. I am trying to find out answer to this problem, but it is a fact that degree of freedom is always 1 if your regression is linear. If it is quadratic, you will see 2. If it is cubic, 3, and so on. Now you need to calculate for residual total sum of square, total degree of freedom as usual, n minus 1. N is your number of pair of observation minus 1. So this is true. This is always true. And then by difference method, you can work out for residual. So n minus 1 minus 1. This minus 1 is for regression. So you get n minus 2. Is it clear? Or now last
Yes.
1 minute is left. I will continue tomorrow. Is it okay for you tomorrow? 9:15? Is it okay, or you have any other class tomorrow? Why don't you speak? You just speak. You have
Sir, we have a class tomorrow.
what time?
Social Science department
What
from
time?
9:15. From
9:15.
9:15 to 10.
So you should speak it. You should. So maybe tomorrow. So maybe evening time tomorrow. Is it okay? Evening tomorrow, 5:15, 5.